Hello everyone, welcome back to this course on multivariable calculus. In this video, we're going to start the concept of integration. So we have seen how to graph functions, we have seen how to study the graphs of functions, the growth of functions using the derivatives, the partial derivatives, we found tangent planes, and now we're going to try to find volumes on the graphs, and that is the first step in doing that is computing double integrals over rectangles, and then later we will see integrals over more complicated regions. So first of all, what are these double integrals? The goal is given a graph of a function and a region. For example, in here is just a rectangle, is a 2 by 2 square. I want to find what is the volume under the graph and above that square. For that, we're going to use the definite integral, and that definite integral is going to be defined in terms of what we call Riemann integrals, which we have seen in one variable. So we're going to do just the same thing, but in two variables. And then we're going to try to figure out how to actually compute those integrals, at least over rectangles. And over rectangles, we are going to do those integrals using iterated integrals. And then we are going to see at the end Fubini's theorem, which is going to tell me that I can actually integrate these in two different ways. I can switch the order of integration and integrate in a couple different ways. So let's start by recalling what is the Riemann integral. The Riemann integral of a function, say y equals f of x, between values a and b is the following. So here is the graph of y equals f of x in blue. This is the graph of the function. And I want to figure out what is the area under the graph, at least between a and b. And what we did is approximate the area first by what we call a Riemann sum, and it's approximated by areas of some rectangles. First, I divided A from the interval from A to B in some equal subintervals, and then at each subinterval, we picked up a point, x1, x2 star, x3 star, xn star, and then evaluated the function, and with that height, we generate rectangles that are going to be close to the graph, but not exactly. There is some error happening, but that is okay because this is just one Riemann sum, and what we're going to do is eventually that delta x, the distance between or the length of a subinterval, is going to decrease to 0, and then these approximations by Riemann sums are actually going to, the limit of those approximations is going to be exactly the area of the graph. So just as a reminder, what this means is that we are going to add the Riemann sum in this case would be a sum from I1 up to n of the sum of areas of those rectangles, which is f of xi star, the height, times the length of the subintervals, which in this case is delta x. So a formula for a Riemann sum would be as follows. What we're going to do is add the area of all those rectangles. Any given rectangle, say this rectangle, the arbitrary one, would be the height is the evaluation of f at the point xi star. So the height of the rectangle is f at the given point in that subinterval times the length of the base. And the length of the base is fixed. In this case, we denote that increment between xi minus 1 and xi by delta x. So that it would be the length of one rectangle, and then we add all of the rectangles. So these would have to go from from the first subinterval to the last subinterval, and this is a Riemann sum. So this here is what we call a Riemann sum, and then we take the limit of this. We're going to take the limit of this as n goes to infinity. When n goes to infinity, there are two things happening. There's more and more subintervals, and also the length of the subinterval would be the length of the subinterval is going to be b minus a divided by n. So the length of the subinterval is also going to decrease. This is going to 0, and this is going to infinity. This is what we call the Riemann integral, the definite Riemann integral, which we denoted by the integral from a to b of f of x dx. Now, sometimes we compute integrals using this limit definition, but this is really cumbersome, and we have formulas and tricks to compute integrals without having to resort to the limit definition, and we are going to do that also in double integrals. So back to the amazing world of multivariable calculus. Suppose now that we have a function of two variables, say, although we can do this for multiple variables, and I want to figure out what is the volume above this rectangle. This rectangle, by the way, right here is the rectangle given by a comma b cross c comma d. What that means is these points x, y on the xy plane such that the x value is bounded between a and b, and the y value is bounded between c and d. And now, given that rectangle, I want to figure out what is the volume above the rectangle and below the graph of the function. And just like we did before, we're going to subdivide this rectangle into a grid of little rectangles and then figure out what is the volume above each one of those rectangles, or approximate it using these boxes. So we break this interval into subintervals, this interval into subintervals. That gives me little boxes, and I'm just going to evaluate at any one point, figure out what the height is, and then just create a box above that little rectangle. That gives me something like this, which is going to be an approximation, a boxy approximation of the graph over that rectangle. And since these are just boxes, I can actually calculate the volume of this whole thing, and that will be an approximation of this. The volume of this is a Riemann integral for these two variable function. So what is a formula for this Riemann integral? Let's do like we did again. So we are going to have first of all, let's figure out what is the area of one of these boxes, or what is the volume of one of these rectangles right here. And what is that? Well, there's going to be delta x and delta y, which is the length of one of these little intervals, the length of one of those little intervals. That gives me the product of the two is the area of this little rectangle. And then I need to evaluate the function at one point that I've chosen arbitrarily inside this little rectangle to give me the height of the box. So that is going to be, I've picked an xi star and a yi star times delta x times delta y. This will be the volume of one of those boxes. And this, by the way, sometimes instead of saying delta x, delta y, we call that also delta delta A, because it's the area of any one of those rectangles. But in any case, this is the volume of one of the boxes, and now I need to add up all the boxes. But now there is, so I can run in this direction, and I have to add all those boxes, and I have to run in this direction and add all those boxes. There is a box here, 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 and then also in here. So there's two parameters to take care of. I have to run over all the j's, and I have to run over all the i's. There might not be even the same number of boxes in one direction or the other. You can see here that there is like 5 in this direction, but there's 8 in this direction. So those might not be the same number of subintervals here or in here, and that is okay. But this approximation, this sum of all these volumes, this is what we call a Riemann sum in the two variable case. So this is one Riemann sum. And then we can take the limit, just like we did before. If I take the limit, and now it is a double limit as n goes to infinity and m goes to infinity, then this will be what we call the Riemann sum, or the Riemann integral in this case, which is, I'm going to denote it as the integral over the region R of my function times dA. So that indicates that is the volume under the graph, if the graph is some positive function in that region, and this is the Riemann integral. This is the Riemann integral in this case, in the two variable case. So for example, in this particular case, in this particular function, f of x, y is equal to 16 minus x squared minus 2y squared over the rectangle, which is the 0, comma 2 cross 0, comma 2. We want to find what is the volume under the graph and above that rectangle. And here we have some approximations. So when there is 4 subintervals in each direction, then the volume is about 41.5. When there is 8 subdivisions, then the volume is this. When there are 16 subdivisions, is this. And you can see that it's getting closer and closer to what the actual graph looks like. And these are going to be better and better approximations of the actual volume. But how do you actually compute that volume? What we do to compute these integrals is first prove properties of integration, which are similar to the properties that the integrals of one variable satisfied, that the integral of sum of two functions is the sum of the integrals, that the integral of a constant times a function is the constant times the integral. If f and is larger than g on that rectangle, then the integral of f is larger than the integral of g. And moreover, if I want to compute this double integral, the entire volume, it turns out you can do it as an iterated integral. So what this means is that I can compute first an integral with respect to x of f between a and b and treat y as a constant in that case, and then compute whatever the result is. I compute an integral with respect to y from c to d. That is what we call the iterated integral, and it is our way to compute integrals at least over rectangles. So we're going to see some examples of this. So let's start with the graph of the function we had in the previous example. Let's compute the actual volume, not just approximations using Riemann sums, but the actual volume under the graph. So we want to find the double integral over this rectangle of the function 16 minus x squared minus 2y squared dA. And what the iterated integrals tells me is that I can compute this as a double integral, first with respect to x, let's say, of 16 minus x squared minus 2y squared. And with respect to x, the bounds are from 0 to 2. So this is 0 to 2. And then I'm going to integrate with respect to y, and the bounds in y are from 0 to 2. So it's going to go from 0 to 2. So I start with just the inside. Let's do the integral from 0 to 2 of 16 minus x squared minus 2y squared dx. And let's see what that is. If I integrate this, the integral of 16 will be 16x plus constants, but we're going to just do a definite integral, so I don't need the constants. The integral of x squared is x cubed divided by 3. And the integral of 2y squared is just another constant, so it's 2y squared x. And now I'm going to evaluate at 0 and 2. So the value at 2 is 16 times 2 minus 2 cubed divided by 3 minus 2y squared times 2. And the value at 0, I'm going to subtract the value at 0, but the value at 0 is 16 times 0 minus 0 divided by 3 minus 2y squared times 0. So that is all zeros. So the answer to this integral is going to be 32 minus 8 divided by 3 minus 4y squared, which is 88 over 3 minus 4y squared. And now I keep going, and now I'm going to integrate from 0 to 2 the result, so 88 divided by 3 minus 4y squared with respect to y. So now the integral of this will be 88 over 3y minus 4y cubed divided by 3, and that evaluated between 0 and 2. So the answer will be 88 divided by 3 times 2 minus 4 times 2 cubed divided by 3 minus the evaluation at 0. 88 divided by 3 times 0 minus 4 y cubed, but the y is now 0, so this is just 0 divided by 3, so that all that in the parentheses is just 0, and what I get is that this is 48. So the volume itself was 48. And you can see from our approximations that the Riemann sums were 41.5, 44.8, 46.4, so they were getting closer and closer to the actual value, which is 48. Let's see another example. So I'm going to start by doing this integral first, and then we will do the second integral. So for this integral, see that we are going to start by integrating with respect to y. So these limits correspond to y, so I can write some parentheses if you want like this. So that is integral with respect to y, with respect to these limits of integration, and then we're going to integrate with respect to x with respect to those limits of integration. So let me start with the integral from 1 to 2 of x squared y dy. That is a constant times y, so the integral will be, the integral of that function will be x squared y squared divided by 2, and that is between 1 and 2. So that is x squared times 4 divided by 2 minus x squared times 1 squared divided by 2. So that is 2x squared minus x squared divided by 2. So that is 3/2 x squared. So that is the answer of the first integral, or the integral within the double integral. So now if I rewrite my integral that I had like this, dy dx, now I know what the inside, the value of the inside is. So now I have to do the integral from 0 to 3 of 3/2 x squared dx. So the integral of that, of 3/2 x squared, the integral of x squared is x cubed divided by 3. So what I get is x cubed, or a half of x cubed, between 0 and 3. And at 3, that will be 3 cubed divided by 2. At 0 is 0 divided by 2. So what I get is 27 divided by 2 for my answer. So let's see what happens now with the second integral. You see that the second integral is the same function, the same bounds, but we have flipped the order of integration. Remember that 0, 3 corresponded to x. So I'm going to integrate first from 0 to 3 with respect to x, and then from 1 to 2 with respect to y. So we have exchanged the order of integration, and let's see if we get the same answer. So I'm going to do that here. I'm going to start with, I'm doing this double integral. Over here, this iterated integral. So I'm going to start with the inside of the integral. That's the integral from 0 to 3 x squared y dx. And with respect to x, that is y times x cubed divided by 3, because that's the integral of x squared. Y is a constant with respect to x, between 0 and 3. And between 0 and 3, I get y times 3 cubed divided by 3 minus y times 0 cubed divided by 3. So that is 9y. Okay, so now I can complete my double integral. I had the integral of x squared y dx dy, and now I know what the inside is. The inside is the integral from 1 to 2 of the inside, which is 9y dy, and that will be 9y squared divided by 2 between 1 and 2, which is 9 times 2 squared divided by 2, plus or minus 9 times 1 divided by 2. So that is 2 times 9 minus 9 halves. So that is 3 halves of 9, which is 27 divided by 2, which is the same answer we got before. Notice that, so the answers coincide, but notice that the work itself is different. The integrals that I had to do is different, and but we did get the same answer. Is that true in general? And the answer is yes. That is called Fubini's theorem, at least for functions that are continuous on that rectangle. A theorem proved by Guido Fubini shows that the area or the volume above that region and below F, it is actually, you can compute it in two different ways and you get the same answer. You can integrate first with respect to y and then with respect to x, or with respect to x and then with respect to y, and you get the same answer no matter what. So we denote then, since it doesn't matter the order, we denote it as an integral, as a double integral over the rectangle dA, and you can compute it in either way. So let's see an example of this. I'm going to integrate the function x minus 3y squared in this rectangle. So first, let's set it up I'm going to integrate first with respect to x, then with respect to y. So the integral with respect to y comes in the outside, and then integral with respect to x, x minus 3y squared. Now dx has to match that the first dx, x has to match with its limits of integration. 0 is between 0 and 2, x is between 0 and 2. So that's why those limits are here. And then dy. So if you want, you can add a parenthesis like this to indicate that now dy, the limits of integration, are between 1 and 2, which matches the limits of integration or the bounds of the rectangle in terms of y. So let's start with the integral from 0 to 2 of x minus 3y squared dx. That will be x squared divided by 2 minus 3y squared x between 0 and 2, which is just the value at 2 because at 0 is 0. So I get 4 divided by 2 minus 6y squared, or simply 2 minus 6y squared. And now I can just integrate this function. So I will get so now I can integrate this function between 1 and 2, 2 minus 6y squared dy. That will be 2y minus 6y cubed divided by 3 between 1 and 2. That is the same as 2y minus 2y cubed between 1 and 2. And that is 4 minus 2 times 2 cubed minus the value at 1, which is 2 minus 2, which is in fact just 0. So what I get is 4 minus 16, so it's minus 12. So that is the answer that I got when I integrated first with respect to x, then with respect to y. Let's do it the other way, see if I still get minus 12 and Fubini's theorem actually works. So now I'm going to integrate first with respect to y, so from 1 to 2 of the function x minus 3y squared dy, and then with respect to x, so the limits with respect to x are now outside and it's between 0 and 2. If I first compute the inside integral with respect to y, what I get is xy minus y cubed between 1 and 2, which is the value at y equals 2, that is 2x minus 8, minus the value at 1, which is x minus 1. So what I get in total is x and minus 8 minus minus 1. So x minus 7 is the function in the inside. After if I've integrated, so this will be the integral now between 0 and 2 of x minus 7 dx, and that is x squared divided by 2 minus 7x between 0 and 2. So just evaluate at 2, that is 2 squared divided by 2 minus 7 times 2. So that is, what is it, 2 minus 14 is minus 12, just like we had calculated before in the other order of integration. So Fubini's theorem works and math wins once again. Let's see another example of an application of Fubini's theorem where it is actually going to really matter how we choose the order of integration. This function y times sine of x times y is continuous, sine is continuous, so this is continuous, the product times y, this is continuous, so Fubini's theorem is going to apply. So now I have to decide if I want to integrate first with respect to y, so integrate from 0 to pi y times sine of xy dy, and then with respect to x, or if I want to integrate first with respect to x, y times sine of xy dx, and then with respect to y. And you see, if I have to do this integral with respect to y times sine of xy, that is an integral that I'm going to have to solve using integration by parts, and I don't want to do that if I can avoid it. But this integral right here is just a constant times sine of x times a constant, so it's essentially just the integral of sine of x. And I know how to do that simply with a u substitution that will work. So let's not do this one, because this one is easy. Okay, so this one is easier, much easier, so let's do that one instead. So first, let's integrate from 1 to 2 y sine of xy dx. The integral of that will be y is a constant times the integral of sine of xy will be minus cosine of xy divided by the constant in front of x. Just like that. You can do that using a u substitution if you want, but that is the integral. This is just minus cosine of xy now between 1 and 2. So now what I get when I evaluate is minus cosine. This is for x equals 2, so I get cosine of 2y minus minus, so plus the cosine of 1 times y, so the cosine of y. All right, so now I can integrate the inside from 0 to pi of the inside is the integral of minus cosine of 2y plus cosine of y dy, which are two easy integrals. The integral of minus cosine of 2y is minus the sine of 2y divided by 2, and the integral of cosine is simply sine of y between 0 and pi. Great. So now I can evaluate this. This is going to be at pi is the sine of 2 pi. The sine of 2 pi is the sine of 0. So I get 0 plus the sine of pi is also 0. So I get another 0 minus the value at 0, but the sine of 0, the sine of 2 times 0, the sine of 0 is also 0, and the sine of 0 is 0. So I get just 0. So the value of the integral is actually just 0, and it was a lot easier to compute it using this order of integration than would have been in this way, where I would have to use integration by parts. Finally, here is a property that we use sometimes in a particular case. If your function is a product of functions, but is a function of x times a function of y, then the double integral actually becomes a product of integrals. Let me show you why. Because when I'm integrating gx hy dx dy, the integral with respect to x, h of y is just a constant multiplying g of x, is a constant with respect to x. So this is h of y times the integral of g of x dx dy. And now this whole thing is just going to be a number. So it's a number multiplying h of y, and it's just going to, I can bring it outside completely of that integral, so becomes an integral with respect to x, which I didn't write the bounds, but this is from a to b, and this is from c to d, etc. And just becomes a product of integrals. So it is not a double integration, it's just an integral with respect to x, an integral with respect to y, and just the product. So let's see this in a particular example. In here, the function is ln y over xy, and I can break this apart into 1 over x times ln y divided by y. So this is a function that only depends on x times a function that only depends on y. So the double integral will be the product of the integrals. So I compute them separately. I can compute with respect to x. Notice that the bounds of integration with respect to x are from 1 to 5. So it is the integral from 1 to 5 of 1 over x dx, and that the integral of that will be the logarithm of x between 1 and 5, and that is the logarithm of 5 minus the logarithm of 1, which is just logarithm of 5. So that is my first integral, and now I have to do the integral of the second one. So ln y divided by y dy, and those bounds are from 1 to 3. And this is, well, ln y over y, if you do, let's see what happens if I, let's try to figure out what that integral is. What happens if I do ln y squared and I take the derivative? The derivative would be 2 ln y times the derivative of ln y, which is 1 over y. So this integral is ln of y squared divided by 2. Between 1 and 3, that is ln of 3 squared divided by 2 minus ln of 1 squared divided by 2, but this is the ln of 1 is 0, so the answer here is ln of 3 squared divided by 2. So overall, over here, the integral of this will be the value of the integral with respect to x times the value of the integral with respect to y multiplied together. So this is the result of that integral. And that's it for integrals over rectangles. And in the next section, we'll do integrals over more interesting regions.